Thank you, Gordon. Bergstrom is, if you're not familiar with Bergstrom, we're a commercial vehicle HVAC specialist. We manufacture the air conditioning units and increasingly systems for commercial vehicles, only we don't manufacture really anything for the automotive industry. We focus on equipment that is generating income or is earning a living and has more of a focus on uptime and reliability from that standpoint. So some of the products that we supply to there are shown, and a few more on this page. So heavy in the on-highway truck industry, some military equipment, ag and off-highway as well. Some of the customers that we do business with there. That customer base has afforded us a fairly broad range of experience with what the commercial vehicle expects, and that's what's really driven this presentation today. So the title then being Electrically Driven Sealed Air Conditioning Systems, Quantum Leap in Reliability. In working with those various customers from those different areas, we've got expectations really that we've come to recognize in three specific areas. Heavy emphasis on the reliability expectations for those customers. The on-highway trucks are looking for 5-year, 500,000 mile hands-off, or even 1 million mile hands-off expectations. They obviously don't want, they're trying to earn a living with those machines, and they don't want those to be down at the side of the road, or to have the operator not driving them because they're not cooling. And very similarly with the off-highway and ag and construction equipment, they want to eliminate vehicle downtime. As is mentioned here, every year in union applications or other applications, it's dramatically different than it was 10 years ago. 10 years ago, maybe the operator was lucky to have a cab. Now, if he doesn't have air conditioning functioning in the cab, he's not going to use it. The machine's going to sit. So that's one of the expectations that we are trying to support from our customers' expectations. Environmental being another aspect. I'm going to talk a little bit more here about on-highway trucks, and particularly some of the no-idle aspects of that are coming about. There's a lot of fuel being used during the idling hours to accomplish the heating and cooling that the drivers need while they're trying to sleep, and a lot of engine emissions being generated during those idle times that doesn't need to be created. And then economic expectations. Weight specifically an expectation obviously for the on-highway truck guys, not so much for the off-highway. Size is a concern for everybody. Return on investment's a concern for everybody. Reduced fuel costs again is an economic concern as well as it's an environmental concern. Engine wear during those idle times specifically, a lot of time spent idling the engine and using up the engine that doesn't need to be done. And then the OE plants have maintenance and processing costs as well. There's a lot of complexity that the plants have in dealing with the HVAC processing and the regulations related to that they'd really rather be free of. When we look at what our challenges are to meet those expectations, again on these three fronts, we look at today's mobile air conditioning system, and we typically have 10 to 12 O-ring leak points. We spend a lot of time at every MACS convention talking about the intensive training that's necessary for the service technicians and the people in the field to service these things correctly and to lubricate the O-rings and to pay attention to cleanliness. And we know that's all in conditions that are less than ideal out in the field for a piece of ag or construction equipment. And we have they always have the same concerns in the plant. They've got to train the plants to process these things correctly and to pay attention to lubricating the O-rings and so forth. So we've got a myriad of opportunities for failure, and I'm sure most of you servicing these things are well aware of these concerns and the problems they lead to. So we've got the O-ring leak points scattered throughout the system. We've got 8 crimped hose fittings. We've got the one rotating shaft seal on the compressor that is a leak point. We've got the belt-driven compressor clutch. We've just heard about some of the issues that always have to be careful of with the belt and then the clutch as well. Most of today's compressors that are used in off-highway and commercial vehicle systems are automotive-based compressors that have been modified to work in a commercial vehicle environment. And it's typically a challenge to make those last as long as the commercial vehicle guys want them to. A little bit different expectation in the automotive. As far as hose permeability, I think we're all well aware of that. It's kind of a double hit for us there for the system in terms of reliability. It's leaking out refrigerant. the flexible lines and particularly the long line lengths that we have on a lot of systems are leaking out refrigerant. So we all know where that leads down the road to low charge and potential compressor failures from that. It's also allowing moisture into the system, and we know we can experience compressor failures from that. And then we also have challenges with compressor speed and life, relating again to the fact that it's really, for the most part, they're adapted automotive compressors trying to survive in an environment that it was not really designed for from the start. Environmental aspects, the challenges really to the no idle is that today's systems require engine operation for that heating and cooling. And then also the permeable hoses also are an environmental issue, as well as the reliability concerns they bring about. And then economics. Field service is high risk due to cleanliness concerns out there. Most of the equipment that, if those of you out there that specialize in servicing off-highway and construction equipment, ag and construction, you probably recognize that a lot of the service equipment was really designed more to be rolled across the GM Goodwrench dealer's floor. It really wasn't designed to survive in the back of your truck headed out to a mine. And that's an issue. Makes it hard for you guys to do the job right. And then we have the OE plant complexity in dealing with their refrigerant processing is another challenge. What Bergstrom has worked on as far as providing solutions to those is specifically at the top there regarding reliability is we want to eliminate those long hose runs and all the opportunity for failures there. That's just way too many variables, and it's not a robust system. If we can go to brazed and sealed lines and a hermetically sealed compressor, we've completely eliminated those care-intensive and training-intensive processes that are done in less than perfect environments, such as out in the field. Another advantage of what I'm going to talk about is the compressor speed can be set as needed. It's no longer tied directly to the engine. So we no longer have to overspeed it or underspeed it to get the capacity that's needed. That has some payoffs in terms of life, and another one that I'll mention here in just a minute. Environmental, regarding no idle specifically, the engine operation isn't required for those significant idling hours of the machine's life. Economics, various items here that are very significant. No refrigerant field service is the intention. That the systems can be fairly small and fairly modular and can be removed, and not that there would be no service performed in the field, but that the refrigerant loop does not need to be tapped into, recharged, recovered, recharged, and rebrazed, for instance, out in the field. Certainly if a motor needs to be replaced or an actuator needs to be replaced, there's still going to be service in the field. But the types of processes that are very cleanliness intensive and maintenance and training intensive could potentially be done much more efficiently and more reliably in the shop environment, where you may have one person who is full-time rebuilding these brazed loops down the road. So we've also got no refrigerant processing at the OE plant. That's something that the OEs are very interested in. Reduced fuel burn during the no idle times and reduced engine wear during the no idle times. And then under the other category, kind of some synergies that come about from this, is some horsepower availability that you can gain from not running the compressor speed and not having it directly linked to engine speed, but choosing to run it at the speed you want for efficiency, not just throwing horsepower at it that you don't need. And then also some cooling package flexibility that the OEs are looking for, specifically with increased engine emission regulations coming. Bergstrom's looked at quite a few competing technologies in trying to come up with those solutions. There's a lot of those there you'll recognize, and ultimately have come up with kind of a three-phase approach that we're taking. The no idle thermal environment, or NITE, the NITE 2, which is the entirely electrified sleeper solution, and then the cab sleeper primary system. And so I'm going to talk about all three of those here in a minute. This chart kind of describes a few of the features and the planned application of those three products. You'll see the NITE column on the left there. It's a sleeper only, a sleeper no idle only, as opposed to one of the differentiators there between NITE and NITE 2. NITE is really designed to maintain the sleeper at the environment that the operator would expect after the existing unit that's in the bunk today, a conventional unit, has pulled it down to that environment. It's planned really for aftermarket to be fit into units, into trucks that right now are facing no idle regulations, and can solve that problem for them. While it will not replace the existing unit, it'll just allow it to, it'll still be there, they'll still use it to pull the cab down, pull the sleeper down to the temperature they want, but they'll no longer have to idle to maintain that. So you see that it's battery powered, fairly low power consumption, moderate capacity, it's available today, and moderate capacity basically in order to allow the reasonably sized batteries to power it for 8 hours plus and still maintain a comfortable environment. As opposed to NITE 2, which is a fully electric sleeper, more of an OE solution, not aftermarket so much. It's intended to go into an OE truck and completely eliminate the conventional unit that's in that sleeper. It's got enough capacity, a little higher capacity, a little higher power consumption, and it can accomplish the pull down as well as the maintaining of that temperature. And then the cab sleeper primary system, which can accomplish the entire cab and bunk cooling needs, heating and cooling needs for a commercial vehicle. And that would obviously be an OEM market, variable power sources, higher power consumption, very high capacity. And we're going to focus right now on NITE and NITE 2, and I'm going to tell you a little bit about the cab sleeper primary systems and some different approaches to getting that done. The NITE and NITE 2 technology are very much scalable up into a full cab sleeper system, or the cab sleeper primary system can be based on a NITE or NITE 2 type technology, but with something that I'm going to refer to as secondary loop technology to give the vehicle designers more flexibility. I want to talk a little bit about why there's this emphasis on solving this no idle issue. You see here some graphic depicting some of the states in the U.S. that currently have no idle laws on the books, and I think this graphic is even a little out of date at the moment. I think it's a few more have been added since then. At the moment, we've got 19 states currently with no idle laws, and federal funding is hanging over their heads and driving more states to pass those laws. And the reasons are fairly clear. We've got a significant amount of pollution being generated by a truck during those idle times. We've got 420 pounds of carbon monoxide a year, 20 tons of carbon dioxide, 250 pounds of nitrous oxide. That's not good, and everybody will recognize some benefits to not creating that pollution. One of the very significant ones up there at the top, one idling truck, and this is not just an idling truck over the course of the year. This is an idling truck just during the idle times, burning about 2,340 gallons of fuel per year. That's about $3,200 of costs there for the fleet or the operator. And even just as important, I think, in the situations we're in right now geopolitically, I think we all recognize we don't really need to be burning that fuel if we don't have to. So there's the Bergstrom NITE system right there. It's a fairly you'll fairly easily recognize. It's a hermetically brazed loop with an electrically driven brushless DC compressor, and you can see that in the booth tomorrow. I want to point out the brushless DC condenser fan, the brushless DC compressor. Both of those are somewhat key to the high efficiency and the ability to run this off of fairly moderate batteries and get 8 hours plus of good performance out of them. Some of the benefits of that, again, is that's a charged, sealed, tested AC system delivered right to the OE. It eliminates over 10 different O-ring joints that have opportunities for failure. It eliminates the OEs having to put on condenser assemblies, run hoses to a compressor assembly and mount that up. It eliminates the compressor clutch that we all know is sometimes a fragile part of the equation. It eliminates the long hose runs and the leak rates that you have and the opportunities for failures you have in those. We think it's going to dramatically help the reduction of field service training by virtue of the fact that we really are going to try and move away from so much refrigerant loop diagnostics and maintenance and processing having to go on in the field, but more of a replace the module, have the refrigerant loop serviced back at your shop potentially, and you'll be maybe doing more rapid repairs of replacing an actuator, replacing a motor, but maybe not intruding into the refrigerant loop. And then also reduced part numbers as well. That in particular is a shot of Bergstrom's cab sleeper primary system there installed on a truck, and that is in fact a secondary loop system that I'll explain here in a moment. There's another picture of it with a diagram. It's got the typical refrigerant components in it, as well as the fact that it's secondary loop means it's got refrigerant to liquid flat plate heat exchangers in there for either the evaporator or the condenser or both. And the secondary loop then pumps the chilled water or hot water to either the front of the vehicle for engine cooling package use, maybe to function as the heat exchanger for the radiator or for the condenser, I mean, or to pump chilled water to the cab to allow that to function as the evaporator would have in a cab. It's also got some air to coolant separators to allow that secondary loop system to work well. So the benefits of this secondary loop technology is if you're going to scale this up to a capacity where you want to be able to cool and heat the entire cab and sleeper area, for instance, if you secondary loop the evaporator, you can reduce the size of the envelope within the cab. I think we've all recognized that there may be, it seems like a good idea to apply electrified technology and use a sealed system, but gosh, you've got to have a pretty big envelope in the cab then, don't you? And one of the answers, if you secondary loop the evaporator, is no, you don't have to have any bigger envelope in the cab. You've got to have a space somewhere. You've already got space in the engine compartment where you had the compressor, so you're kind of reallocating this space. You've got to group most of it in one spot, but it doesn't have to be in the cab. You can provide them the kind of cab design flexibility that they're accustomed to today, and the primary unit can be remote. And if you just secondary loop the evaporator, that primary unit still got the refrigerant loop in it, still have to provide condenser airflow to that primary unit. Now if you secondary loop the condenser, you reduce the size of that primary unit envelope again, and you allow flexibility in mounting the primary unit. It doesn't need condenser airflow now. You might tuck it back somewhere on the truck where it doesn't need condenser airflow, and you've got a remotely package now that you can scooch around and maybe mount to the engine cooling package in the front where it may get the airflow it needs. And then obviously to provide the ultimate flexibility, you can secondary loop both. So just to provide a little graphic depiction of what I'm describing there, there's your typical conventional distributed HVAC loop where you've got these various components not contained within any one box, but you've got the system spread around the machine and refrigerant flow going counterclockwise there. Now if you secondary loop the evaporator, you've still got the refrigerant loop here, but instead of an evaporator where the heat is being exchanged between air and the evaporator, you're exchanging heat between the evaporator and glycol solution, and you're pumping that, and you're exchanging that heat through a flat plate type heat exchanger, and you're pumping that then to the cab. That allows you to locate this wherever you want to on the machine. Now in this instance you still need to have cooling airflow for the condenser, but this unit can be separate from this, and you don't have refrigerant connections between the two. You may have hose clamps, but you're pumping chilled water now to the cab. Now contrast that, the same concept, but if you secondary loop the condenser, you've still got your refrigerant circuit here, but instead of the condenser here exchanging to air, you're exchanging to the same liquid, not the same liquid actually, it's be a separate circuit, and you're pumping that then to a remote unit that is operating as your heat exchanger for the condenser. And then to provide ultimate flexibility, may not be the most cost-effective to have a double secondary loop, but it certainly provides the most flexibility for the instances where it's needed, where you can have a tightly contained and take advantage of all the benefits that the sealed electrically driven system can provide in this unit here, and locate it where you have space to locate it, and then pump coolant to accomplish your heat rejection for the condenser in a remote unit, and accomplish your cooling through the chilled water for the cabs in a remote unit in the cab. So that's Bergstrom secondary loop. I'm going to focus now the rest of the presentation on the NITE system. Some of the concepts that were looked at that resulted in Bergstrom settling on this NITE system, you see represented here. We've got the NITE system here, the auxiliary power systems, meaning a genset, thermal storage solutions, and electrified truck stops all have opportunity to solve these problems that we've gone through. The thing I want to focus on is really the weight instances. Gensets are quite heavy, some drawbacks there. Thermal storage is very heavy. Now the electrified truck stops are obviously no weight penalty to the truck, but the infrastructure required to get truck stops to that point is going to be slow in coming and expensive. And the payback period is also something that's worth mentioning there, that we see pretty good payback opportunity, and we think this system is going to take on, become popular from that standpoint as well. We've already covered some of these points, the why there's this drive in the government towards no idle, the waste in money, the excess petroleum, the air pollution. Are going to focus on the fuel consumption and the pollution. Current practice for trucks, 458,000 trucks out there traveling more than 500 miles from home. This is all kind of summarizing what's the population of trucks out there, and why is it such a problem that this solution has been created. This source for this data comes from the Argonne National Laboratory. And the industry sources estimate that about 6 hours a day, those trucks, those 458,000 trucks, are idling. It varies. In the winter it's up to 10 hours a day, in the summer it's as little as 4.5. So the average is about 6 hours a day. And so that totals per truck about 1,830 hours per year that trucks are idling. And you take that times the 458,000 trucks out there that are traveling far enough from home every day that they're spending the night somewhere. That's 840 million gallons of diesel fuel that's being consumed annually. That's a lot of diesel fuel. That's, as I've said, in today's political climate, we don't need that sort of fuel consumption if it can be avoided. Now, in order to run through, just to kind of walk through why we think this system tends to pay for itself from an economic standpoint, it takes about a gallon of fuel to idle for an hour, and take that times the 1,830 hours that a truck is idling, you get about 1,830 gallons there, and the average price per gallon comes up to about $2,500 in fuel savings that is going up in smoke. And then we've also got the expense for preventive maintenance and for engine overhauls due to the idling time. A lot of time spent with the engine running. Obviously it's burning the fuel, and it's using up engine component life as well. So you got total cost idle there of about $2,800. Some of the states there specifically that have the no idle regulations. There's a graphic depiction of the system. It is a fuel-fired heater. There's the refrigerant loop, and representation of it in the truck. Ductwork and controls, and the battery set up there, located potentially on a frame rail there. Some performance test results. You'll see that the outside ambient, a little over 90 F, and the goal for the system, as I've said, is to maintain a comfortable temperature in the sleeper area after the existing cab sleeper, after the existing sleeper conventional system has drawn it down. And so you'll see the temperature in the bunk area was maintained just a little under 75. That's an average for the mattress head, lap, and foot area for 7 hours or so, 7 hours plus before the system was shut off. And this next graph shows a little bit about this particular data is power consumption. You'll see it's being monitored very closely and is varying up and down. The system is a lot of work has gone into making sure that the system is not expending any unnecessary energy, so that we can get the 8 hours plus of life out of it without having larger than necessary batteries and larger than necessary weight and investment there. Some of the validation testing that's going on for the system, fairly extensive. Field validation as well. Several of these systems, quite a few out on various fleets. We've got data loggers on them and have been measuring quite a bit of information. Go over some of the feedback right now from some of the drivers. They're much to our very happy with the fact that they're telling us that it's given them plenty of cold air, too cold at times. We are exceeding 8 hours of system operation. We are, and this was, I think, some of the tougher tests in terms of being able to maintain temperatures are in daytime operations, where you still have pretty high temps. Daytime ambience of 96 F, the sleeper is still comfortable. Airflow direction and quantity is good. Operation from 4 a.m. till noon, where you're experiencing a sunrise and a growing load, we're still able to maintain a comfortable environment there. System's very quiet, low vibration. They're saying they like the control. Drivers are recommending that the fleets install more systems. There's one of the installations. See, it's very unobtrusive in the cabin environment. There's an installation under a mattress back wall. See the majority of the refrigerant loop is parked there underneath the mattress with the ductwork extending up and the controls there. Batteries down on the frame rail, and there's a close-up of the ductwork and the controls. So as the advertisement depicts there, we've kind of combined some of the things that you all have probably been inventing out there on your own to allow people to potentially come up with no idle solutions. Tried to wrap that up into something that's been validated and designed for the commercial vehicle applications. So we'd like to see you stop by the Bergstrom Kysor booth. Actually, it's referred to as the Kysor booth, I believe, in the programs, and it's available there, booth 1304. Thank you very much.
Thanks, Tim. Very enlightening presentation. As we've said before, these afternoon sessions at MACS are attempting to show you guys some new ground, so to speak. Our next presenter, Ed Eaton, is Chief Engineer at Amalgatech Coolant. They have a fuel and oil testing facility located in Phoenix, Arizona. He's going to talk to us about coolant usage in heavy-duty and diesel vehicles. Please put your hands together and welcome Ed.